Right now, as you listen to these words, time itself is moving differently across our solar system. On Jupiter, the largest planet orbiting our Sun, every hour that passes equals only 59 minutes here on Earth. This isn't science fiction. This isn't a measurement error. This is the fundamental nature of reality, confirmed by the most precise atomic clocks ever built and proven by decades of space exploration. For centuries, humans believed time was absolute. We thought 1 second on Earth equaled 1 second everywhere, else in the universe. Isaac Newton described time as flowing uniformly, like an invisible river carrying all of existence at the same steady pace. Albert Einstein shattered this assumption in 1915 with his theory of general relativity, revealing that massive objects literally bend the fabric of spacetime itself. The more massive an object, the more it warps time around it. Jupiter, with its immense gravitational field, creates a temporal environment so different from Earth that astronauts traveling there would experience time at a measurably different rate. Every hour spent in Jupiter's vicinity would pass more slowly relative to Earth. When they returned home, they would have aged slightly less than people who remained on our planet. This isn't theoretical physics confined to textbooks. NASA's Juno spacecraft, currently orbiting Jupiter, experiences this time dilation effect every moment of its mission. The implications stretch far beyond academic curiosity. Understanding gravitational time dilation is essential for GPS satellite accuracy, future interplanetary travel, and our comprehension of how the universe operates at its most fundamental level. Without accounting for these relativistic effects, GPS systems would accumulate errors of several miles per day. Astronauts planning missions to Jupiter must factor time dilation into every aspect of mission planning, from communication delays to biological aging calculations. Scientists have measured Jupiter's gravitational time dilation using atomic clocks accurate to 1 part in 18 quintillion. These instruments, sensitive enough to detect the time difference caused by moving a clock just 18 centimeters higher on Earth, confirm that Jupiter's massive presence creates a measurable temporal distortion throughout the solar system. The Cassini spacecraft, during its Jupiter flyby in 2000, provided additional confirmation when mission controllers detected the predicted time dilation effects in the spacecraft's radio signals. This discovery connects to even more mind-bending realities: black holes, the universe's most extreme gravitational environments, stretch time dilation to its breaking point. An astronaut falling toward a black hole would experience time almost normally, while distant observers would watch them appear to slow down and freeze at the event horizon. Jupiter's time dilation is mild compared to these cosmic extremes, but it represents the same fundamental physics governing everything from neutron stars to the expansion of spacetime itself. The mathematics underlying this phenomenon emerged from Einstein's insight that gravity isn't a force pulling objects together, but rather the curvature of spacetime caused by mass and energy. Massive objects like Jupiter create what physicists describe as a gravitational well in the fabric of spacetime. Time moves more slowly at the bottom of these wells, creating the measurable differences between Earth time and Jupiter time. As we explore Jupiter's time dilation tonight, we'll discover how this seemingly abstract physics concept affects practical space exploration, why it proves we live in a universe far stranger than everyday experience suggests, and what it reveals about the true nature of time itself. We'll examine the precise measurements that confirm this effect, explore its implications for future space travel, and understand how Jupiter's gravitational influence extends throughout the entire solar system. If you're fascinated by the hidden physics governing our solar system, subscribe and hit the thumbs up button. And what do you think it would feel like to experience time differently on another world? Comment below, I'll pin the most thoughtful answer. The story of Jupiter's time dilation begins with understanding why massive objects bend spacetime, but it leads us to profound questions about reality, consciousness, and our place in a universe where time itself is relative. Every tick of every clock on Earth is synchronized differently than every tick on Jupiter, creating a cosmic symphony of temporal variations that most people never realize exists. When you check the time after watching this video, remember that this same moment is unfolding differently throughout the solar system. On Jupiter, Time moves at its own pace, governed by the immutable laws of physics that Einstein revealed over a century ago. This isn't just a curiosity for physicists. It is a fundamental aspect of the reality we inhabit, hiding in plain sight within our own solar system. Now let's begin our journey into the strange world of gravitational time dilation, starting with the basic physics that makes Jupiter's temporal environment so different from our own. Warped spacetime. Einstein's general theory of relativity fundamentally changed our understanding of gravity and time by revealing that massive objects don't just attract other objects. They literally bend the fabric of spacetime itself. This concept, initially difficult to visualize, becomes clearer when we imagine spacetime as a flexible surface. Place a massive object like Jupiter on this surface, and it creates a depression, a gravitational well that affects everything nearby. The mathematical framework describing this phenomenon emerged from Einstein's field equations. Published in 1915, these equations demonstrated that mass and energy warp the geometry of spacetime, creating what we experience as gravitational effects. And like Newton's description of gravity as an attractive force between objects, Einstein showed that objects follow the curved paths through spacetime created by mass and energy distributions. Jupiter, with a mass 2.5 times greater than all other planets in our solar system combined, creates a significant gravitational well. This massive planet contains 1.9 times kilograms of matter, concentrated in a volume that, while large, still creates an average density of 1.3 to 6 grams per cubic centimeter. This enormous mass distribution curves spacetime throughout the Jovian system, affecting not only the orbits of Jupiter's moons but also the rate at which time passes. The relationship between mass and spacetime curvature follows precise mathematical laws. Einstein's field equations describe how matter and energy create curvature, while geodesic equations describe how objects move through curved spacetime. These equations predict that time passes more slowly in stronger gravitational fields, an effect known as gravitational time dilation. Measuring this effect requires extraordinary precision. The time dilation on Jupiter compared to Earth is approximately 1 part in a billion. This means that for every billion seconds, about 32 years that pass on Earth, Jupiter experiences about 999,999,999 seconds. While this difference seems minuscule, it's measurable with modern atomic clock technology and has practical implications for space missions. The European Space Agency's JUICE mission, scheduled to arrive at Jupiter in 2031, will carry atomic clocks specifically designed to measure these relativistic effects. These instruments will help scientists better understand Jupiter's internal structure by detecting tiny variations in gravitational time dilation caused by the planet's uneven mass distribution. Dense regions within Jupiter will create slightly stronger gravitational fields, producing measurable time dilation variations. Understanding spacetime curvature also explains why Jupiter's time dilation affects the entire Jovian system differently. Jupiter's largest moons, Io, Europa, Ganymede, and Callisto, experience varying degrees of time dilation depending on their orbital distances. Io, orbiting closest to Jupiter at 421,700 kilometers, experiences stronger gravitational time dilation than Callisto, which orbits at 1,882,700 kilometers. The physics becomes even more interesting when considering Jupiter's rotation. The planet spins once every 9 hours and 56 minutes, creating additional relativistic effects. This rotation produces frame dragging, a phenomenon where massive rotating objects literally drag spacetime around with them. Frame dragging creates additional complications for precise time measurements, as it affects the motion of objects orbiting Jupiter. Gravitational Probe B, a NASA mission that operated from 2000 to 2005, successfully measured frame dragging around Earth. Jupiter's much larger mass and faster rotation create frame dragging effects thousands of times stronger than Earth's. Future missions to Jupiter must account for these effects in their navigation systems and scientific instruments. The mathematical description of Jupiter's spacetime curvature involves the Schwarzschild metric, modified to account for the planet's rotation and internal structure. This metric describes the geometry of spacetime around a massive, rotating object like Jupiter. From this mathematical framework, scientists can calculate precise time dilation effects and predict how spacecraft trajectories will be affected by Jupiter's gravitational field. Experimental confirmation of these predictions comes from multiple sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided extensive data on gravitational effects throughout the Jovian system. Radio signals from Galileo, analyzed for Doppler shifts caused by gravitational time dilation, confirmed theoretical predictions within measurement uncertainties. The Juno mission, currently orbiting Jupiter, carries even more precise instruments for measuring gravitational effects. Juno's radio science experiment uses Earth-based antennas to track tiny changes in the spacecraft's velocity caused by Jupiter's gravitational field variations. These measurements reveal Jupiter's internal structure while simultaneously confirming relativistic predictions about time dilation and spacetime curvature. Modern understanding of Jupiter's spacetime environment comes from combining Einstein's theoretical framework with precise observational data. The planet's gravitational field varies with depth, creating a complex three-dimensional map of spacetime curvature near Jupiter's core, where pressures exceed 4,000 gigapascals and temperatures reach 20,000 Kelvin. The extreme matter density creates the strongest gravitational fields in the solar system outside the Sun. This foundational understanding of spacetime curvature sets the stage for exploring how time dilation manifests throughout the Jovian system. The mathematics may be complex, but the underlying principle is elegant. Massive objects reshape the very fabric of reality, creating environments where time itself flows at different rates. Massive planet Jupiter's extraordinary mass makes it a gravitational giant that dominates the outer solar system and creates the time dilation effects we observe. To understand why Jupiter affects time differently than Earth, we must examine the sheer scale of this planetary colossus and how its mass distribution creates such powerful gravitational fields. Jupiter contains 71% of all planetary mass in our solar system. If you combined every other planet, moon, asteroid, and comet into a single object, Jupiter would still be 2.5 times more massive. This enormous mass concentration minus 317, 8 times Earth's mass, packed into a volume roughly 321 times larger than Earth, creates an average gravitational acceleration of 24.79 meters per second square. D at Jupiter's cloud tops compared to Earth's 9.81 meters per second squared. The planet's internal structure contributes significantly to its gravitational dominance. Jupiter likely contains a rocky core roughly 10 to 20 times Earth's mass, surrounded by a layer of liquid metallic hydrogen extending to about 0.8 Jupiter AD. Above this lies a thick atmosphere of molecular hydrogen and helium, with trace amounts of methane, ammonia, and other compounds. This layered structure creates a complex gravitational field that varies with depth and location. Understanding Jupiter's mass requires examining its formation history. The planet formed approximately 4.6 billion years ago during the early solar system's gas and dust accretion phase, and like terrestrial planets that formed primarily from rocky materials, Jupiter accumulated vast quantities of hydrogen and helium directly from the solar nebula. This process continued until Jupiter reached sufficient mass to gravitationally bind these light elements, preventing them from escaping to space. Precise measurements of Jupiter's mass come from analyzing spacecraft trajectories as they pass through the planet's gravitational field. The Voyager 1 and 2 flybys in 1979 provided early, precise measurements, while subsequent missions including Galileo, Cassini, and Juno have refined these values. Current measurements place Jupiter's mass at 1.89813 times 1,027 kilograms, with an uncertainty of only about 0.01%. This massive gravitational field creates measurable effects throughout the solar system. Jupiter's influence extends far beyond its immediate vicinity, affecting asteroid orbits, comet trajectories, and even the orbital characteristics of other planets. The gravitational relationship between Jupiter and the Sun creates Lagrange points, locations where gravitational forces balance, allowing objects to maintain stable positions relative to both bodies. The planet's rapid rotation, completing one full rotation every 9 hours and 56 minutes, adds complexity to its gravitational field. This rotation creates an oblate shape, where Jupiter's equatorial diameter exceeds its polar diameter by about 9,276 kilometers. The resulting gravitational field variations produce additional relativistic effects beyond simple time dilation, including frame dragging and gravitational wave generation. Jupiter's four largest moons, the Galilean satellites discovered by Galileo Galilei in 1610, orbit within this intense gravitational environment. Io experiences tidal forces so extreme that sulfur volcanoes constantly resurface the moon. Europa's subsurface ocean exists because Jupiter's gravitational heating prevents the water from freezing solid. Ganymede, the largest moon in the solar system, generates its own magnetic field through interactions with Jupiter's magnetosphere. The gravitational interactions between Jupiter and its moons create measurable time dilation variations. Throughout the system, each moon experiences slightly different gravitational time dilation depending on its orbital distance and position during close approaches to Jupiter. These moons experience stronger gravitational fields and correspondingly greater time dilation effects. Modern space missions use these gravitational variations for scientific investigation and spacecraft navigation. The technique called gravity assist, or gravitational slingshot, allows spacecraft to gain or lose velocity by carefully timing their passage through planetary gravitational fields. The Cassini mission used Jupiter's gravity in 2000 to accelerate towards Saturn, while simultaneously conducting scientific observations of the Jovian system. Measuring Jupiter's gravitational field requires extraordinary precision. The Juno spacecraft carries a gravity science instrument that detects gravitational field variations as small as 1 part in a billion by monitoring tiny changes in the spacecraft's velocity. These measurements reveal Jupiter's internal structure, including the size and composition of its rocky core and the distribution of heavy elements throughout its interior. The relationship between Jupiter's mass and its time dilation effects follows directly from Einstein's general relativity equations. The gravitational time dilation factor depends on the gravitational potential, which is proportional to mass divided by distance. Jupiter's enormous mass creates a gravitational potential deep enough to produce measurable time dilation effects that persist throughout the planet's sphere of influence. Comparing Jupiter's gravitational environment to Earth's reveals the dramatic differences in spacetime curvature. While Earth's surface gravity produces time dilation effects of about 1 part in a billion per meter of altitude, Jupiter's surface gravity creates time dilation effects roughly 2.5 times stronger. This difference becomes significant for precision timekeeping and navigation systems operating in the Jovian environment. Jupiter's gravitational influence extends beyond simple time dilation to affect fundamental physics experiments. Scientists studying gravitational waves, particle physics, and cosmology must account for Jupiter's gravitational effects when designing sensitive instruments. The LISA gravitational wave detector, planned for deployment in space, will need to consider Jupiter's gravitational influence on its precision measurements. The planet's mass also affects light propagation through the solar system. Einstein's theory predicts that massive objects bend the path of light rays passing nearby, an effect called gravitational lensing. While Jupiter's gravitational lensing effects are too small to observe directly from Earth, they become significant for spacecraft navigation and radio astronomy observations conducted near Jupiter. This massive planetary environment creates the foundation for understanding why time passes differently on Jupiter than on Earth. The enormous concentration of matter in Jupiter's structure warps spacetime sufficiently to create measurable temporal effects that influence everything from spacecraft operations to fundamental physics research throughout the solar system. Time flows. The measurement of time dilation around Jupiter represents one of the most precise confirmations of Einstein's general relativity in our solar system. Using atomic clocks accurate to billionths of a second and radio tracking systems that can detect velocity changes smaller than a millimeter per hour, scientists have verified that time indeed flows differently in Jupiter's gravitational environment. Atomic clocks provide the fundamental tool for measuring gravitational time dilation. These devices, based on the precisely defined oscillations of cesium atoms, maintain accuracy to 1 part in 1015 or better. This extraordinary precision allows scientists to detect the tiny time differences caused by gravitational fields. A cesium atomic clock transported from Earth's surface to Jupiter's cloud tops would run measurably slower due to the stronger gravitational field. The mathematics of gravitational time dilation follows from the metric tensor describing curved spacetime around massive objects. For weak gravitational fields like those in the solar system, the time dilation factor can be approximated using the Newtonian gravitational potential. The ratio of time intervals measured by distant observers compared to local observers near a massive object depends on the difference in gravitational potential between their locations. Specifically, the time dilation factor between Earth and Jupiter involves calculating the gravitational potential difference between the two locations. Jupiter's gravitational potential at its cloud tops is approximately 2.5 times deeper than Earth. As at sea level, this potential difference creates a measurable time dilation effect where clocks near Jupiter run slower than identical clocks on Earth. Radio tracking of spacecraft provides practical measurements of these relativistic effects as spacecraft orbit Jupiter. Ground-based antennas monitor their radio signals for Doppler shifts that reveal velocity changes caused by gravitational acceleration. These measurements must account for gravitational time dilation effects to accurately determine spacecraft positions and velocities. The Galileo mission, which operated in the Jovian system from 1995 to 2003, provided extensive data on relativistic effects. Ground controllers carefully analyzed radio signals from the spacecraft to measure gravitational redshift, the frequency change experienced by electromagnetic radiation climbing out of gravitational wells. These measurements confirm theoretical predictions within experimental uncertainties. Gravitational redshift represents the electromagnetic signature of time dilation. Light waves climbing out of strong gravitational fields lose energy and shift toward longer, redder wavelengths. Conversely, light waves falling into gravitational wells gain energy and shift toward shorter, bluer wavelengths. The magnitude of these frequency shifts directly measures the gravitational time dilation between the mission and reception locations. The Juno mission, currently orbiting Jupiter, carries advanced radio science equipment specifically designed to measure relativistic effects with unprecedented precision. The spacecraft's radio system can detect frequency changes as small as a few millihertz, allowing scientists to measure gravitational time dilation effects throughout Jupiter's complex gravitational field. Variations in Jupiter's gravitational field create measurable differences in time dilation at different locations within the system. The planet's non-spherical shape, rotation, and internal mass distribution produce a complex gravitational environment where time flows at slightly different rates depending on position and altitude. These variations provide valuable information about Jupiter's internal structure and composition. The concept of proper time versus coordinate time becomes crucial for understanding these measurements. Proper time represents the time interval measured by a local observer using local clocks, while coordinate time represents the time interval measured by distant observers using their reference frame. Gravitational time dilation describes the relationship between proper time and coordinate time in curved spacetime. Experimental verification of Jupiter's time dilation effects requires careful analysis of multiple data sources. Scientists combine radio tracking data, atomic clock measurements, and theoretical calculations to separate relativistic effects from other factors affecting spacecraft motion, solar radiation pressure, magnetic field interactions, and thermal effects must all be accounted for to isolate pure gravitational time dilation. The practical implications of these time dilation effects extend beyond academic physics to impact space mission planning and execution. Communication delays between Earth and Jupiter orbiting spacecraft include relativistic corrections that account for gravitational time dilation. Navigation systems must incorporate these effects to maintain accurate position determinations throughout long-duration missions. Future missions to Jupiter will carry even more sophisticated timing systems to study relativistic effects. optical atomic clocks. Based on electronic transitions in neutral atoms rather than hyperfine transitions in cesium, promise accuracy improvements of 100-fold or more. These advanced clocks will enable detailed mapping of Jupiter's gravitational field through precise time dilation measurements. The relationship between time dilation and gravitational redshift provides multiple ways to measure the same underlying physics. Electromagnetic radiation carries timing information that reveals gravitational effects on both the propagation of light and the flow of time. Comparing these measurements provides robust confirmation of relativistic predictions. Ground-based observations also contribute to understanding Jupiter's time dilation effects. Very Long Baseline Interferometry (VLBI) uses networks of radio telescopes to track spacecraft positions with extraordinary precision. These measurements can detect the subtle effects of gravitational time dilation on radio signal propagation times between spacecraft and Earth-based receivers. The temporal environment around Jupiter varies continuously as the planet rotates and orbits the Sun. Jupiter's 12-year orbital period creates long-term variations in its distance from Earth, affecting the magnitude of observed time dilation effects. The planet's rapid rotation produces additional frame-dragging effects that complicate simple time dilation calculations. Modern theoretical frameworks combine Einstein's general relativity with post-Newtonian approximations to predict precise time dilation effects throughout the solar system. These calculations account for the gravitational influences of multiple bodies, including the Sun, Earth, and Jupiter itself, to provide accurate predictions for spacecraft navigation and scientific observations. Understanding how time flows differently around Jupiter opens the door to exploring the broader implications of these relativistic effects for space exploration, fundamental physics, and our comprehension of the universe's temporal structure. The precise measurements confirming these effects represent humanity's growing ability to test the most fundamental laws of physics in the extreme environments of space. Precision measurement. Measuring Jupiter's gravitational time dilation requires instrumentation capable of detecting temporal variations smaller than the blink of an eye, spread across decades of observation. The technological achievement of confirming Einstein's predictions around Jupiter represents one of the most precise physics experiments ever conducted in space, involving atomic clocks, radio astronomy, and spacecraft navigation systems operating at the limits of measurement accuracy. Atomic clock technology forms the foundation of relativistic time measurements. Modern cesium fountain clocks achieve frequency stability of 1 part in 1016. Meaning they would gain or lose less than 1 second over 300 million years. This extraordinary precision emerges from measuring the microwave frequency corresponding to transitions between two hyperfine levels of the cesium-133 ground state, defined as exactly 9,192,631,770 Hz. The development of space-qualified atomic clocks specifically for gravitational experiments required overcoming numerous technical challenges. These devices must maintain their precision while withstanding launch vibrations, temperature extremes, radiation exposure, and the vacuum of space. The Deep Space Atomic Clock, tested aboard the General Atomics Orbital Testbed spacecraft, demonstrated atomic clock operation in space with stability comparable to ground-based laboratory standards. Radio science experiments provide the primary method for measuring gravitational time dilation during spacecraft missions. These investigations use coherent radio links between spacecraft and Earth-based antennas to detect tiny frequency changes caused by relativistic effects. The technique requires phase-stable radio systems capable of maintaining coherence over signal travel times exceeding an hour for Jupiter missions. The mathematics underlying these measurements involves analyzing Doppler shifts in spacecraft radio signals to extract gravitational effects from orbital dynamics. As spacecraft move through Jupiter's gravitational field, their velocities change according to Newtonian mechanics, producing Doppler shifts proportional to the line-of-sight velocity component. Gravitational time dilation introduces additional frequency shifts that must be separated from purely kinematic effects. Ground-based atomic clock networks provide the reference standards for measuring relativistic effects in space. The International Atomic Time Scale, maintained by the International Bureau of Weights and Measures, coordinates approximately 450 atomic clocks worldwide to establish the most stable time reference. Available, GPS satellites carry atomic clocks that must be corrected for relativistic effects to maintain synchronization with this terrestrial timescale. The Galileo spacecraft's radio science investigation provided early precision measurements of gravitational effects in the Jovian system during the mission's 8-year operation. Scientists accumulated thousands of hours of radio tracking data to measure Jupiter's gravitational field with unprecedented accuracy. These measurements confirmed general relativity predictions while revealing details of Jupiter's internal structure. Separating gravitational time dilation from other physical effects requires sophisticated data analysis techniques. Solar radiation pressure on spacecraft creates small but measurable accelerations that must be modeled and removed from radio tracking data. Thermal effects on spacecraft equipment introduce frequency drifts that can mask relativistic signatures, magnetic field interactions, and charged particle impacts create additional noise sources. The Juno mission represents the current state of the art in precision gravitational measurements. The spacecraft carries a gravity science investigation that uses radio tracking to map Jupiter's gravitational field with resolution sufficient to determine whether the planet has a solid core. This investigation requires measuring spacecraft velocity changes as small as 10 to 6 meters per second, equivalent to detecting the motion of a fingernail growing. Advanced signal processing techniques enable extraction of relativistic effects from noisy spacecraft data. Kalman filtering algorithms combine multiple data sources to estimate spacecraft states while accounting for various error sources. Maximum likelihood estimation methods identify the most probable gravitational field parameters consistent with observed radio tracking signatures. Optical atomic clocks promise even greater precision for future gravitational experiments. These devices, based on electronic transitions in neutral atoms rather than microwave transitions, achieve frequency stabilities approaching 1 part in 1019. Aluminum ion clocks, ytterbium lattice clocks, and strontium lattice clocks all demonstrate performance improvements over traditional cesium standards. The planned laser interferometer space antenna LISA mission will carry precision timing systems capable of detecting gravitational waves through spacetime distortions measured with femtometer accuracy. These systems must account for all relativistic effects, including gravitational time dilation, to achieve the sensitivity required for gravitational wave astronomy from space. Frequency transfer systems enable comparison of atomic clocks separated by astronomical distances. Optical frequency combs provide precise frequency references that can be transmitted via laser links between spacecraft and Earth. Two-way frequency transfer protocols eliminate many systematic errors by using bidirectional signal propagation to separate clock differences from propagation delays. The international scientific community maintains databases of atomic clock measurements spanning decades to study long-term relativistic effects. The International Earth Rotation and Reference Systems Service coordinates global timing observations to provide reference standards for space navigation and fundamental physics experiments. Quantum clock technologies under development promise revolutionary improvements in timing precision. Ion trap clocks using highly charged ions achieve reduced sensitivity to environmental perturbations. Nuclear transition clocks based on thorium-229 nuclei could provide references immune to electromagnetic field variations that limit current atomic clock performance. Statistical analysis of precision timing measurements requires careful attention to systematic errors and correlated noise sources. Allen variance analysis characterizes clock stability over different time scales, revealing the optimal integration times for achieving minimum measurement and certainty. Bayesian inference methods combine prior knowledge with observational data to extract maximum information about gravitational parameters. Verification of gravitational time dilation measurements involves cross-correlation analysis using independent experimental techniques. Lunar laser ranging experiments provide complementary tests of general relativity using Earth-Moon system dynamics. Pulsar timing arrays offer natural cosmic clocks for studying gravitational wave backgrounds and testing relativistic theories, the technological capabilities enabling precision measurement of Jupiter's time dilation effects continue advancing rapidly. Future missions will carry atomic clocks orders of magnitude more precise than current space-qualified standards, enabling tests of general relativity and measurements of fundamental physics parameters with unprecedented accuracy throughout the solar system and beyond. These precision measurement techniques reveal the remarkable accuracy with which Einstein's century-old theory describes reality, while opening new frontiers for understanding gravity, time, and the fundamental structure of spacetime through direct experimental investigation of the universe's most extreme environments. Orbital effects. Jupiter's gravitational time dilation extends far beyond the planet itself, creating a complex temporal environment that affects every object orbiting within the Jovian system. The four Galilean moons Io, Europa, Ganymede, and Callisto each experience different rates of time passage based on their orbital distances, while dozens of smaller moons contribute to an intricate gravitational dance where time flows at subtly different rates throughout three-dimensional space. Io, the innermost Galilean satellite, orbits Jupiter at an average distance of 421,700 kilometers and experiences the strongest gravitational time dilation in the system. At this distance, time passes approximately 0.3 parts per billion slower than at infinite distance from Jupiter. While this difference seems negligible, it accumulates to measurable effects over the timescales of space missions and becomes significant for precision navigation and communication systems. Europa orbits at 671,034 kilometers, experiencing gravitational time dilation roughly 60% as strong as Io. The Moon's subsurface ocean, heated by tidal flexing from Jupiter's gravitational field, exists in an environment where time passes differently than on Earth's surface. Future missions to Europa must account for these temporal differences when planning scientific observations and data transmission schedules. Ganymede, at 1,070,412 kilometers from Jupiter, represents a fascinating case study in orbital gravitational effects. As the largest moon in the solar system, Ganymede generates its own magnetic field through a liquid iron core. The interaction between Ganymede's magnetosphere and Jupiter's creates complex electromagnetic environments where both gravitational and electromagnetic effects influence timekeeping and navigation systems. Callisto, the outermost Galilean satellite at 1,882,709 kilometers, experiences the weakest gravitational time dilation but still shows measurable effects compared to Earth-based reference frames. The Moon's heavily cratered surface records billions of years of solar system history, with each impact event occurring in a slightly different temporal environment as Callisto's orbit evolved over geological time. The orbital mechanics of Jupiter's moon system create time-varying gravitational fields throughout the region, as moons move through their elliptical orbits. Their distances from Jupiter change continuously, creating corresponding variations in gravitational time dilation. These orbital dynamics must be precisely modeled for spacecraft navigation and scientific data interpretation. Resonant orbital relationships between Jupiter's moons add complexity to the temporal environment. The 4:2:2:1 orbital resonance between Io, Europa, and Ganymede means these moons return to the same relative configuration every 7.16 days. During these alignments, gravitational interactions create tidal bulges and orbital perturbations that influence local gravitational fields and corresponding time dilation effects. Spacecraft operating in the Jovian system experience continuously changing gravitational time dilation as they navigate between moons and through different orbital altitudes. The Galileo mission's varied trajectory, including multiple flybys of different moons at various distances, provided extensive data on how gravitational time dilation varies throughout three-dimensional space around Jupiter. The concept of gravitational binding energy becomes crucial for understanding orbital time effects. Each moon exists in Jupiter's gravitational well, with its binding energy determining the local gravitational potential and corresponding time dilation. More tightly bound objects experience stronger gravitational fields and greater time dilation effects. Tidal effects create additional complications in the gravitational environment around Jupiter. The planet's enormous gravitational field stretches objects along the Jupiter-facing direction while compressing them perpendicular to this axis. These tidal forces vary as the inverse cube of distance, creating gravitational field gradients that influence both orbital mechanics and relativistic effects. The rotation of Jupiter itself contributes frame-dragging effects throughout the orbital system. As the massive planet spins, it literally drags spacetime around with it, creating additional relativistic effects beyond simple gravitational time dilation. These frame-dragging effects influence the precession of orbital planes and the behavior of gyroscopes carried by spacecraft. Precise orbit determination in the Jovian system requires accounting for relativistic effects at multiple levels. Classical Newtonian orbital mechanics provides the primary framework, but relativistic corrections become necessary for precision navigation and scientific observations. These corrections include gravitational time dilation, gravitational redshift, frame dragging, and light time effects. The Jupiter system serves as a natural laboratory for testing general relativity under conditions impossible to replicate on Earth. The large mass, extended system of moons, and accessible orbital environment provide opportunities to measure relativistic effects that complement laboratory experiments and astronomical observations of more extreme objects like neutron stars and black holes. Future missions to the Jovian system will carry increasingly sophisticated instruments for measuring relativistic orbital effects. The European Space Agency's JUICE mission, scheduled to arrive at Jupiter in 2031, will carry precision tracking equipment capable of measuring gravitational effects throughout its planned orbital tour of the Galilean satellites. Communication systems operating in the Jovian environment must account for relativistic effects on radio signal propagation. Signals traveling between spacecraft and moons experience gravitational redshift as they climb out of planetary and satellite gravitational wells. Light time corrections must include relativistic effects on signal propagation speeds and curved spacetime. The long-term evolution of Jupiter's moon system involves gravitational effects that operate over millions of years. Tidal dissipation gradually changes orbital characteristics, while gravitational interactions between moons create secular perturbations that slowly modify the system's configuration. Understanding these long-term effects requires incorporating relativistic corrections into dynamical models. Spacecraft trajectory design for Jupiter missions involves optimizing paths through the complex gravitational environment while accounting for relativistic effects. Gravity assist maneuvers use planetary gravitational fields to change spacecraft velocities, with relativistic corrections ensuring accurate trajectory predictions and mission planning. The measurement of orbital gravitational effects provides valuable information about Jupiter's internal structure. Variations in gravitational time dilation throughout the system reveal mass distribution within the planet, including the size and density of Jupiter's core and the distribution of heavy elements throughout its interior. Ground-based observations contribute to understanding orbital relativistic effects through radio astronomy techniques. Very long baseline interferometry (VLBI) can track spacecraft positions with extraordinary precision, detecting the subtle signatures of gravitational time dilation and frame dragging effects in SPACE-CRAFT orbital motion. The Jupiter system's orbital environment demonstrates how gravitational time dilation creates a complex temporal landscape where time flows at different rates depending on location and motion. Through three-dimensional space, understanding these effects becomes increasingly important as space exploration expands to include long-duration missions and permanent installations throughout the solar system. Navigation challenges. Navigating spacecraft through Jupiter's gravitational environment presents extraordinary challenges that require accounting for relativistic effects at every stage of mission planning and execution. The combination of strong gravitational fields, complex orbital dynamics, and precise scientific requirements demands navigation systems capable of maintaining accuracy, despite temporal variations that would confuse conventional guidance systems. The fundamental challenge emerges from the need to coordinate multiple reference frames operating under different gravitational conditions. Earth-based mission control operates in terrestrial gravitational time, while spacecraft near Jupiter experience measurably different time flow rates. Communication delays between these reference frames compound the complexity, as commands sent from Earth arrive at spacecraft operating in a different temporal environment. GPS technology, which revolutionized navigation on Earth, becomes useless in the Jovian system due to the absence of orbital navigation satellites. Instead, spacecraft must rely on Deep Space Network (DS) and tracking stations that use radio ranging and Doppler measurements to determine position and velocity. These measurements must incorporate relativistic corrections to maintain the accuracy required for precise orbital maneuvers and scientific observations. Radio signal propagation through Jupiter's gravitational field experiences measurable effects that navigation systems must account for. Electromagnetic radiation climbing out of gravitational wells experiences gravitational redshift, while signals falling into gravitational wells experience gravitational blue shift. The magnitude of these frequency shifts provides information about gravitational field strength but also introduces corrections needed for accurate ranging measurements. The concept of coordinate time versus proper time becomes crucial for navigation system design. Mission planners on Earth use coordinate time based on terrestrial atomic clock standards, while spacecraft instruments operate according to proper time in their local gravitational environment. Navigation algorithms must constantly translate between these time standards to maintain accurate position and velocity determinations. Spacecraft autonomous navigation capabilities become essential for operations in the Jovian system due to communication delays exceeding 1 hour at maximum Earth-Jupiter separation. Autonomous navigation systems must incorporate relativistic models to maintain accuracy while operating independently of Earth-based corrections. These systems use onboard instruments including star trackers, inertial measurement units, and sometimes atomic clocks to maintain navigation solutions. Trajectory planning for Jupiter missions requires numerical integration of spacecraft motion through complex gravitational fields while accounting for relativistic effects. The n-body problem describing motion in the Sun-Jupiter-Moon system becomes significantly more complex when relativistic corrections are included. Modern trajectory design uses high-precision numerical integration algorithms that incorporate general relativistic effects. Gravity-assist maneuvers, essential for efficient interplanetary travel, must account for relativistic effects to achieve planned velocity changes. As spacecraft pass close to massive bodies like Jupiter, they experience strong gravitational acceleration and corresponding time dilation effects. The precise timing and geometry of these encounters require relativistic calculations to ensure successful execution. The Galileo mission demonstrated the challenges and solutions for precision navigation in the Jovian system during its 8-year operational period. The spacecraft conducted multiple close flybys of Jupiter's moons while maintaining communication with Earth despite varying communication delays and relativistic effects. Mission navigators developed sophisticated techniques for managing these challenges. Optical navigation techniques provide complementary position information independent of radio tracking. Spacecraft cameras can image Jupiter's moons against background star fields to determine relative positions with high precision. These optical measurements must account for light time effects and gravitational lensing to achieve maximum accuracy. The Juno mission represents current state-of-the-art navigation capabilities in the Jovian environment. The spacecraft's highly elliptical polar orbit takes it from 4,300 kilometers above Jupiter's cloud tops to over 8 million kilometers at apopsis. Navigation through this extreme orbital environment requires continuous adaptation to changing gravitational conditions and corresponding relativistic effects. Spacecraft attitude control systems must account for gravitational gradient effects that become significant in Jupiter's strong gravitational field. Large spacecraft experience differential gravitational acceleration across their structure, creating torques that must be compensated by attitude control thrusters or reaction wheels. These gravitational gradient effects also influence the behavior of precision instruments. Future missions to Jupiter will face even greater navigation challenges as scientific requirements demand increasingly precise positioning accuracy. The planned Europa Clipper mission must navigate through Jupiter's radiation environment while conducting close flybys of Europa's surface. This mission requires navigation accuracy sufficient to target specific surface features while avoiding hazardous radiation zones. Autonomous orbit determination capabilities enable spacecraft to maintain accurate navigation solutions without continuous Earth-based tracking. These systems use Kalman filtering algorithms that combine multiple sensor inputs with dynamical models to estimate spacecraft states. Incorporating relativistic effects into these algorithms requires careful attention to computational efficiency and numerical stability. Communication system design must account for relativistic effects on signal propagation times and frequencies. Deep space network stations use sophisticated signal processing techniques to extract navigation information from spacecraft signals while compensating for gravitational redshift, Doppler effects, and propagation delays through curved spacetime. The development of quantum navigation technologies promises revolutionary improvements in spacecraft positioning accuracy. Quantum inertial sensors using atom interferometry could provide navigation references immune to many environmental effects that limit current navigation systems. These devices would still require relativistic corrections but could offer unprecedented accuracy in gravitational field measurements. Formation flying missions in the Jovian system present particularly challenging navigation requirements. Multiple spacecraft operating in close proximity must maintain precise relative positions while accounting for differential gravitational effects and relativistic corrections. The complexity increases exponentially with the number of spacecraft and the precision requirements of formation. Geometry. Landing missions on Jupiter's moons face unique navigation challenges during descent and surface operations. The Huygens probe's successful landing on Titan demonstrated techniques for precision entry, descent, and landing in outer solar system environments. Future missions to Europa or Ganymede must adapt these techniques for the specific gravitational and environmental conditions of Jupiter's moons. Ground-based support for Jupiter mission navigation requires international cooperation through organizations like the International Astronomical Union. Coordinate systems and time standards must be precisely defined and maintained to ensure compatibility between different mission elements and ground support systems worldwide. The lessons learned from Jupiter navigation challenges apply broadly to future deep space exploration missions. As human spaceflight expands beyond Earth orbit, understanding and managing relativistic effects in navigation systems becomes essential for mission safety and success. The techniques developed for Jupiter missions provide the foundation for navigation throughout the solar system and beyond. Space missions. Every spacecraft mission to Jupiter must contend with the practical reality that time passes differently in the Jovian environment, affecting everything from communication schedules to scientific data collection timing. The history of Jupiter exploration reveals how mission planners have adapted to these relativistic effects, developing techniques and technologies that enable successful operations despite the temporal complexities of the giant planet's gravitational environment. The Pioneer 10 and 11 missions, launched in 1972 and 1973 respectively, provided humanity's first direct experience with Jupiter's gravitational effects on spacecraft operations. While these early missions lacked the precision timing systems to directly measure relativistic effects, mission controllers observed subtle anomalies in communication timing that hinted at the temporal variations predicted by general relativity. Voyager 1 and 2, launching in 1977, carried more sophisticated timing and communication systems that enabled the first practical measurements of relativistic effects during Jupiter encounters. The mission's radio science experiments used coherent radio links to measure Doppler shifts and signal propagation delays that revealed both gravitational acceleration effects and the subtle signatures of gravitational time dilation. The Galileo mission, Arriving at Jupiter in 1995 marked a new era in understanding and managing relativistic effects during extended operations in the Jovian system. During its 8-year orbital mission, Galileo's instruments accumulated thousands of hours of data while operating in Jupiter's time-dilated environment. Mission planners developed sophisticated scheduling systems that accounted for the temporal differences between Earth and Jupiter reference frames. Communication protocols for Jupiter missions must account for both classical light time delays and relativistic effects. Radio signals traveling between Earth and Jupiter experience travel times ranging from 33 minutes at closest approach to 54 minutes at maximum separation during these propagation times. Signals also experience frequency shifts due to gravitational redshift as they climb out of Jupiter's gravitational well. Scientific instrument timing becomes critical when operating in Jupiter's gravitational environment. Many experiments require precise coordination between multiple instruments or comparison with Earth-based observations. The Galileo atmospheric probe, for example, transmitted data during its descent through Jupiter's atmosphere, while mission controllers on Earth synchronized observations with ground-based telescopes and space-based instruments. The Cassini spacecraft's Jupiter flyby in 2000 demonstrated advanced techniques for managing relativistic effects during gravity assist maneuvers. The spacecraft used Jupiter's gravitational field to accelerate towards Saturn while simultaneously conducting scientific observations. Precise timing of instrument operations required accounting for gravitational time dilation effects throughout the encounter. Data storage and transmission systems on Jupiter missions must accommodate the temporal complexities of operating in curved spacetime. Spacecraft computers timestamped scientific data using onboard clocks that operate in Jupiter's gravitational time, while ground systems receive and process this data according to Earth's temporal reference frame. Converting between these time systems requires sophisticated software algorithms. The Juno mission, currently orbiting Jupiter, represents the state-of-the-art in managing relativistic effects during planetary exploration. The spacecraft's highly elliptical orbit creates continuously varying gravitational conditions that affect instrument timing and data collection. Mission operators have developed adaptive scheduling systems that automatically adjust for changing relativistic conditions throughout each orbit. Autonomous operation capabilities become essential for Jupiter missions due to communication delays and relativistic effects that complicate real-time control from Earth. Spacecraft must execute complex sequences of scientific observations and orbital maneuvers based on pre-programmed instructions that account for predicted gravitational conditions and timing variations. The New Horizons mission's Jupiter flyby in 2007 provided valuable experience with high-speed encounters through Jupiter's gravitational field. Although the spacecraft's primary destination was Pluto, its Jupiter encounter served as a critical navigation and instrument calibration opportunity while demonstrating techniques for rapid data collection in relativistic environments. Future missions to Jupiter will face even greater challenges as scientific requirements become more demanding and mission durations extend. The European Space Agency's JUICE mission, scheduled to launch in 2023, will conduct detailed studies of Jupiter's icy moons over several years. This extended operation period requires sophisticated systems for managing cumulative relativistic effects on scientific observations. Landing missions present unique challenges for managing relativistic effects during critical mission phases. The proposed Europa lander missions must execute precision descents to the surface while operating in Jupiter's gravitational environment. Navigation and guidance systems for these missions require real-time relativistic corrections to ensure successful landings. Multi-spacecraft missions in the Jovian system create additional complexity for managing temporal coordination. Future missions might deploy multiple orbiters, landers, or atmospheric probes that must coordinate their activities despite operating at different distances from Jupiter and experiencing different gravitational time dilation effects. The development of atomic clock technology specifically for space missions enables more precise management of relativistic effects. The Deep Space Atomic Clock, demonstrated aboard the General Atomics Orbital Test Bed, provides timing references stable enough to enable autonomous navigation without continuous reference to Earth-based time standards. Mission planning software incorporates increasingly sophisticated models of relativistic effects throughout the solar system. These tools enable mission designers to predict and account for gravitational time dilation, frame dragging, and other general relativistic effects when planning spacecraft trajectories and scientific observation schedules. Sample return missions from Jupiter's moons present particular challenges for managing relativistic effects across multiple mission phases. Spacecraft must collect samples in Jupiter's gravitational environment, store them during the return journey, and deliver them to Earth where analysis occurs in a different temporal reference frame. Maintaining sample integrity and measurement traceability requires careful attention to temporal coordination. International cooperation in Jupiter exploration requires standardization of timekeeping systems and coordinate frames that account for relativistic effects. Organizations like the International Astronomical Union maintain precise definitions of coordinate systems and time standards that enable collaboration between different space agencies and research institutions. The lessons learned from decades of Jupiter missions provide essential experience for future exploration of other massive planets and exotic gravitational environments. As space exploration expands to include neutron stars, black holes, and other extreme objects, the techniques developed for managing relativistic effects at Jupiter will serve as the foundation for even more challenging missions. Ground-based support systems for Jupiter missions require continuous upgrades to maintain the precision necessary for managing relativistic effects. The Deep Space Network's tracking stations use atomic clocks and sophisticated signal processing equipment to extract navigation and scientific information from spacecraft signals affected by gravitational time dilation and other relativistic phenomena. The technological and operational advances driven by Jupiter exploration have applications far beyond planetary science, contributing to fundamental physics research, precision timing systems, and navigation technologies that benefit scientific research and practical applications throughout the solar system and on Earth. Communication delays. The vast distances between Earth and Jupiter create communication delays that fundamentally change how mission controllers operate spacecraft in the Jovian system. These delays, ranging from 33 to 54 minutes for radio signals traveling at light speed, combine with gravitational time dilation effects to create complex temporal coordination challenges that require innovative solutions for spacecraft command and control. Radio signals traveling between Earth and Jupiter must propagate through the solar system's gravitational environment, experiencing subtle but measurable effects from the Sun's gravitational field and Jupiter's own massive presence. General relativity predicts that electromagnetic radiation experiences frequency shifts and propagation delays when traveling through curved spacetime, effects that become significant for precision timing and navigation applications. The baseline communication delay results from the finite speed of light and the enormous distances involved in interplanetary communication. At closest approach, when Jupiter and Earth are on the same side of the Sun, radio signals require approximately 33 minutes to travel between the planets. At maximum separation, when Jupiter and Earth are on opposite sides of the Sun, communication delays extend to 54 minutes or more. Mission control centers must adapt their operational procedures to accommodate these extended communication delays. Traditional real-time spacecraft control becomes impossible when every command requires over an hour for a complete communication cycle. Instead, mission controllers develop detailed command sequences that spacecraft execute autonomously, with periodic status updates providing confirmation of successful operations. The Deep Space Network (DSN), operated jointly by NASA, the European Space Agency, and other international partners, provides the ground-based infrastructure for communicating with Jupiter missions. DSN stations in California, Spain, and Australia maintain continuous coverage as Earth rotates, ensuring round-the-clock communication capabilities despite the planet's rotation. Gravitational effects on radio signal propagation become measurable for Jupiter communications due to the precision required for spacecraft navigation and scientific observations. As signals travel from Earth toward Jupiter, they experience gravitational acceleration in the Sun's gravitational field, while signals traveling from Jupiter toward Earth climb out of both Jupiter's and the Sun's gravitational wells. The phenomenon of gravitational redshift affects the frequency of radio signals traveling between Earth and Jupiter. Signals climbing out of gravitational wells lose energy and shift toward lower frequencies, while signals falling into gravitational wells gain energy and shift toward higher frequencies. These frequency shifts must be accounted for in communication system design and signal processing algorithms. Command uplinking to spacecraft requires sophisticated scheduling systems that account for communication delays and relativistic effects. Mission controllers must predict spacecraft positions and attitudes at the time commands will be received and executed, rather than at the time commands are transmitted. This prediction requires accurate models of spacecraft orbital dynamics and environmental effects. Data downlinking from Jupiter missions presents different challenges, as spacecraft must buffer scientific data and spacecraft telemetry for extended periods before transmission opportunities become available. High-gain antennas on spacecraft must be precisely pointed toward Earth to achieve the signal strength necessary for reliable communication across interplanetary distances. The concept of light time correction becomes crucial for accurate spacecraft navigation and scientific coordination. Light time represents the propagation delay for electromagnetic signals traveling between 2 points in space. For Jupiter missions, light time corrections account for both geometric delays due to distance and relativistic delays due to gravitational effects. Autonomous spacecraft operations become essential when communication delays make real-time control impossible. Jupiter mission spacecraft carry sophisticated computer systems capable of executing complex sequences of scientific observations, orbital maneuvers, and system maintenance operations without continuous guidance from Earth-based controllers. Emergency response procedures for Jupiter missions must account for the impossibility of immediate communication with Earth. Spacecraft fault protection systems automatically respond to anomalous conditions using pre-programmed safing procedures that protect the spacecraft while awaiting instructions from mission controllers. These systems must be robust enough to handle unexpected situations autonomously. Communication system reliability becomes critical for Jupiter missions due to the long distances involved and the impossibility of immediate technical support from Earth. Spacecraft typically carry redundant communication systems and multiple backup procedures to ensure continued contact with Earth despite equipment failures or environmental challenges. The Galileo mission's communication challenges illustrate the complexities of managing information flow across interplanetary distances. The spacecraft's high-gain antenna failed to deploy properly, forcing mission controllers to rely on a low-gain antenna with much lower data transmission rates. Despite this setback, the mission successfully operated for 8 years by developing innovative data compression and transmission techniques. Network coding and error correction become essential technologies for reliable communication across interplanetary distances. Radio signals traveling through space experience interference from solar radiation, cosmic rays, and other sources that can corrupt data transmission. Advanced error correction codes enable reconstruction of original data despite significant corruption during transmission. Real-time science operations require careful coordination between spacecraft instruments and Earth-based observatories to maximize scientific return despite communication delays. Coordinated observations of dynamic phenomena on Jupiter or its moons must account for light time delays to ensure proper synchronization between space-based and ground-based observations. The development of laser communication systems promises significant improvements in data transmission rates for future Jupiter missions. Optical communication systems can achieve data rates orders of magnitude higher than traditional radio systems, enabling transmission of larger volumes of scientific data despite the long distances involved. Relay communication architectures using multiple spacecraft could potentially reduce effective communication delays for future Jupiter exploration. Spacecraft positioned at intermediate points between Earth and Jupiter could relay messages, reducing overall communication delays and providing backup communication paths for critical mission operations. International cooperation in Jupiter mission communications requires coordination of ground station resources and communication protocols. The Committee on Space Research (COSPAR) and other international organizations develop standards for interplanetary communication that enable cooperation between different space agencies and research institutions worldwide. Communication security becomes increasingly important for Jupiter missions as space exploration expands and becomes more competitive. Encrypted communication protocols protect sensitive mission data and prevent unauthorized access to spacecraft control systems, while maintaining the openness necessary for scientific collaboration and international cooperation. Future communication technologies under development include quantum communication systems that could provide ultra-secure data transmission across interplanetary distances. These systems use quantum entanglement and other quantum mechanical phenomena to create communication channels that are fundamentally immune to interception or interference. The experience gained from managing communication delays and relativistic effects during Jupiter missions provides essential knowledge for future exploration of even more distant destinations. Missions to Saturn, Uranus, Neptune, and eventually interstellar space will face even greater communication challenges that build upon the techniques developed for Jupiter exploration. Ground-based communication infrastructure continues evolving to support increasingly ambitious Jupiter missions. Next-generation deep space network stations will incorporate larger antennas, more powerful transmitters, and advanced signal processing capabilities to enable communication with smaller spacecraft at greater distances while maintaining the precision necessary for navigation and scientific operations. Future implications and understanding of gravitational time dilation around Jupiter opens extraordinary possibilities for future space exploration and fundamental physics research. As humanity develops more sophisticated spacecraft and extends missions deeper into the solar system, the lessons learned from Jupiter's temporal environment will prove essential for navigation, communication, and scientific investigation in even more extreme gravitational conditions. Atomic clock networks distributed throughout the solar system could provide unprecedented precision for testing general relativity and studying fundamental physics. By placing atomic clocks on Jupiter, its moons, and other planetary bodies, scientists could create a solar system-wide timing network capable of detecting gravitational waves, measuring planetary masses with extraordinary precision, and testing alternative theories of gravity. The planned Laser Interferometer Space Antenna LISA mission will use precision timing to detect gravitational waves from space, operating in the solar system's gravitational environment. LISA must account for time dilation effects from the Sun, Earth, and other massive bodies. The experience gained from managing relativistic effects at Jupiter directly contributes to LISA's technical requirements and operational procedures. Future human missions to Jupiter and its moons will face unprecedented challenges in managing biological and psychological effects of differential time flow. Astronauts spending extended periods in Jupiter's gravitational environment will experience measurable time dilation relative to Earth, raising complex questions about aging, medical monitoring, and psychological adaptation to different temporal environments. The concept of gravitational time banking emerges as a theoretical possibility for advanced civilizations by strategically placing objects or habitats in different gravitational environments. It might be possible to create temporal advantages where some activities occur in slow time environments while others proceed normally. This concept has implications for data storage, manufacturing processes, and long-term scientific observations. Advanced propulsion systems under development could utilize gravitational slingshot maneuvers around Jupiter to achieve velocities approaching significant fractions of light speed. At such velocities, special relativistic effects would combine with gravitational time dilation to create complex temporal environments that spacecraft designers must understand and manage for. Successful interstellar missions. The search for extraterrestrial intelligence SETI must account for how gravitational time dilation affects communication attempts with civilizations that might exist in different gravitational environments. Signals from civilizations near massive objects would arrive redshifted due to gravitational effects, while their perception of time might differ significantly from our Earth-based reference frame. Quantum technology applications in high-gravity environments like Jupiter's vicinity could reveal new physics phenomena. Quantum clocks, quantum computers, and quantum communication systems operating in strong gravitational fields might exhibit behaviors impossible to study on Earth, potentially leading to discoveries about the relationship between gravity and quantum mechanics. The development of closed ecological systems for long-duration Jupiter missions requires understanding how gravitational time dilation affects biological processes, plant growth cycles, microbial metabolism, and human circadian rhythms might all respond differently to the temporal environment around Jupiter, necessitating new approaches to life support system design. Mining operations on Jupiter's moons could encounter unexpected challenges related to time dilation effects, precision timing for automated mining equipment, coordination between surface operations and orbital facilities, and synchronization of transportation schedules all become more complex when operating in environments where time flows at different rates. Scientific instrument calibration becomes increasingly complex as missions venture into regions with significant gravitational time dilation. Instruments calibrated on Earth or in Earth orbit must be recalibrated when operating in Jupiter's gravitational environment to maintain measurement accuracy and traceability to terrestrial standards. The emerging field of gravitational wave astronomy benefits directly from understanding time dilation effects throughout the solar system. Ground-based gravitational wave detectors like LIGO and Virgo must account for temporal variations caused by Earth's orbital motion through the Sun's gravitational field, while space-based detectors face even greater challenges in extreme gravitational environments. Educational implications of Jupiter's time dilation extend far beyond physics classrooms. Understanding that time passes differently throughout the solar system challenges fundamental assumptions about the nature of reality and encourages students to think more deeply about the relationship between matter, energy, space, and time. Commercial space ventures planning operations in the Jupiter system must factor relativistic effects into business models and operational procedures. Communication delays, navigation challenges, and temporal coordination issues all affect the cost and complexity of commercial activities in the outer solar system. International space law must evolve to address questions about legal and contractual issues arising from time dilation effects when contracts specify deadlines or schedules. Which time reference frame applies? How do legal systems account for aging differences between individuals who spend time in different gravitational environments? The philosophical implications of experiencing different rates of time passage could profoundly affect human consciousness and culture. Astronauts returning from extended missions to Jupiter might have aged measurably less than people who remained on Earth, creating new categories of human experience and challenging traditional concepts of shared temporal reality. Advanced manufacturing processes might exploit gravitational time dilation for precision applications, chemical reactions, crystal growth, or other processes that require extended time periods could potentially be accelerated or decelerated by operating in appropriate gravitational environments, opening new possibilities for materials science and manufacturing technology. Backup civilization concepts for ensuring human survival might incorporate strategic use of gravitational time dilation by establishing colonies in different gravitational environments. Humanity could create temporal diversity that provides resilience against catastrophic events affecting Earth or other settlements. The development of artificial gravity systems for spacecraft becomes more complex when operating in environments with significant natural gravitational time dilation. Engineers must consider how rotation-induced artificial gravity interacts with gravitational time dilation to create habitable environments for human crews during extended missions. Navigation systems for future interstellar missions will build upon techniques developed for managing relativistic effects in the Jupiter system. As spacecraft velocities increase towards significant fractions of light speed, special relativistic effects will combine with gravitational effects to create navigation challenges that require precise understanding of spacetime geometry. Precision agriculture and space habitats must account for how gravitational time dilation affects plant growth and development, crop rotation schedules, planting timing, and harvest coordination all become more complex when operating in environments where biological processes proceed at different rates relative to Earth-based agriculture. The potential for discovering exotic physics phenomena increases as human activities extend into regions of strong gravitational fields. Jupiter's environment might provide natural laboratories for studying physics beyond the standard model, gravitational effects on quantum systems, or other phenomena impossible to investigate under terrestrial conditions. These future implications demonstrate how understanding Jupiter's gravitational time dilation extends far beyond academic physics to influence practical aspects of space exploration, human settlement of the solar system, and our fundamental understanding of reality itself. The knowledge gained from studying temporal effects at Jupiter provides the foundation for humanity's expansion into the cosmos and our continued investigation of the universe's deepest mysteries. Cosmic perspective. Jupiter's gravitational time dilation represents just one example of the universe's far stranger temporal landscape, where time flows at dramatically different rates near black holes, neutron stars, and other exotic objects. Understanding Jupiter's relatively mild time effects provides a gateway to comprehending the extreme temporal environments that exist throughout the cosmos and the profound implications for our understanding of reality itself. Black holes create the universe's most extreme time dilation effects, where the flow of time approaches zero at the event horizon. An object falling into a stellar mass black hole would experience time normally from its own perspective, while distant observers would watch it appear to slow down and freeze at the event horizon. Jupiter's time dilation, significant by solar system standards, pales in comparison to these cosmic extremes. Neutron stars, with densities exceeding nuclear matter and gravitational fields billions of times stronger than Earth's, create time dilation effects thousands of times more pronounced than Jupiter. A neutron star with 1 point for solar masses compressed into a sphere 20 kilometers in diameter creates surface time dilation where 1 hour might correspond to several hours for distant observers. The cosmic expansion itself affects the flow of time on the largest scales. General relativity shows that time passes differently in expanding spacetime compared to static reference frames. While these cosmological effects are negligible for human timescales, they become significant when considering the evolution of the universe over billions of years. Gravitational waves, ripples in spacetime itself, create temporary time dilation effects as they pass through space. These waves, detected by LIGO and Virgo observatories, cause minute variations in the rate of time passage as they stretch and compress spacetime. Jupiter's gravitational field represents static spacetime curvature, while gravitational waves represent dynamic curvature propagating at light speed. The concept of cosmic time emerges from cosmological models that describe the universe's evolution. In the standard cosmological model, there exists a preferred time coordinate associated with the cosmic microwave background radiation's rest frame. This cosmic time provides a universal reference against which all other time measurements can be compared. Quasars and active galactic nuclei, powered by supermassive black holes containing millions or billions of solar masses, create extreme gravitational environments where time dilation effects dominate local physics. Material falling into these black holes experiences time dilation so severe that processes occurring near the black hole appear dramatically slowed when observed from Earth. The Large Hadron Collider creates artificial gravitational effects through acceleration that produce measurable time dilation for subatomic particles. These particles, accelerated to velocities approaching light speed, experience time dilation due to special relativity that can be directly measured and compared with theoretical predictions. Understanding gravitational time dilation helps physicists interpret these particle physics experiments Cosmic strings, hypothetical one-dimensional defects in spacetime predicted by some theories of particle physics, would create unique gravitational effects including time dilation around their enormous linear mass density. While cosmic strings have never been definitively observed, their predicted gravitational effects would create time dilation patterns unlike anything produced by conventional matter. The multiverse concept, suggesting that our observable universe might be one of many universes with different physical laws, raises questions about whether time flows similarly in other universes. If different universes have different gravitational constants or other fundamental parameters, the relationship between matter and spacetime curvature might differ dramatically. Dark matter, which comprises approximately 85% of all matter in the universe, contributes to gravitational effects and corresponding time dilation throughout cosmic structure. Galaxies embedded in dark matter halos experience gravitational time dilation effects from this invisible matter component that can only be detected through its gravitational influence. The first milliseconds after the Big Bang involved extreme densities and gravitational fields that created time dilation effects far exceeding anything observed in the current universe. Understanding these primordial conditions requires extending general relativity to energy scales, where quantum gravitational effects become important. Primordial black holes, potentially formed during the early universe's extreme conditions, could exist with masses ranging from subatomic to stellar scales. These exotic objects would create time dilation effects proportional to their masses, with microscopic primordial black holes producing negligible effects while stellar mass primordial black holes would rival conventional black holes. The anthropic principle suggests that universe's physical constants, including those determining gravitational strength and corresponding time dilation effects, must be compatible with the emergence of complex structures and life. If gravity were significantly stronger or weaker, time dilation effects would be dramatically different, potentially preventing the formation of stable planetary systems. Wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe, would create complex time dilation effects for travelers passing through them. Depending on the wormhole's geometry and the gravitational fields at its entrances, travelers might experience significant time differences relative to external observers. The holographic principle, emerging from studies of black hole physics, suggests that information content of any region of space can be encoded on its boundary surface. This principle has profound implications for understanding time and causality in gravitational environments, suggesting that time dilation effects might reflect fundamental information processing limits in curved spacetime. Quantum gravity theories attempt to unify general relativity with quantum mechanics, potentially revealing new physics that modifies time dilation effects at extremely small scales or in extremely strong and gravitational fields. These theories might predict departures from Einstein's predictions in regimes where quantum effects become significant. The cosmic web, the largest scale structure in the universe consisting of interconnected filaments of matter separated by vast voids, creates a complex gravitational landscape where time dilation varies depending on location within this structure. Galaxy clusters at the intersections of cosmic web filaments experience stronger gravitational fields and correspondingly greater time dilation. Vacuum metastability, the possibility that our universe's vacuum state might not be the lowest energy configuration possible, could lead to dramatic changes in physical laws and corresponding time dilation effects. If a vacuum decay event occurred, such events would propagate at light speed, creating expanding regions where physics operates under different rules. The measurement problem in quantum mechanics, concerning how quantum superpositions collapse into definite states, might be related to gravitational effects and time dilation. Some theories suggest that gravitational time dilation plays a role in quantum state reduction, connecting the macroscopic world of general relativity with the microscopic world of quantum mechanics. These cosmic perspectives demonstrate that Jupiter's gravitational time dilation, while significant for solar system exploration, represents just a tiny glimpse into the universe's vast temporal diversity, from the extreme time dilation near black holes to the subtle effects of cosmic expansion The universe operates according to principles that make time itself a dynamic, variable quantity rather than the fixed backdrop that everyday experience suggests. Understanding these cosmic time effects becomes increasingly important as human technology becomes more precise and our exploration extends beyond the solar system. The lessons learned from studying Jupiter's gravitational environment provide essential preparation for encountering the far more extreme temporal landscapes that await throughout the universe.